In this section, we're going to start taking a look at being able to approximate definite integrals using three various numerical methods. And there are a number of other numerical methods, but these are sort of like the standard ones that people use to approximate definite integrals. So I'm going to go through these one by one. And the first one we're going to do is probably one that you remember from Calc 1, maybe. It's going to be the midpoint rule. And essentially what we do is we take the midpoint of each of these rectangles to represent the height. Because as a left endpoint, there might be some underestimate, and a right endpoint, there might be overestimate. And so this kind of tries to put an average of those estimates together. So we have our delta x, which is going to be the base, b minus a over n, where b is the terminal point. So right here would be b on this end, and over here would be a at this end point. And so what we're trying to do is we're just trying to basically figure out how wide each of the bases are. And then the height of the rectangle is going to be represented by f at x bar for each of those, or x bar I, if you would. So let's just take a look at a couple examples of working with the midpoint rule. And then in the next video, we'll look at the trapezoidal rule. I'll kind of give an overview of it and then kind of define what's going to be a couple example problems. And then Simpson's rule, same thing. All right, so we have this integral sine x over x from 1 to 3 in the x-axis. All right. And so obviously, this is going to be an integral that we can't compute by using analytic methods. All right. So we're going to sketch the graph of the above area, and then we're going to construct a definite integral. So I know the definite integral is easy. So 1 to 3 sine x over x dx. And the area for this, what we can do is we can just use Wolfram alpha. All right, so I'm just going to go ahead and pull that up so that way we can kind of see what we can do for the area as well as the approximation. All right, so we're just going to go to Wolfram alpha. And we're just going to type in sine of x divided by x. All right, and we're going to get a graph. All right, so here's our graph. In fact, so over, let's see if we can type this in, and maybe it'll give us the exact graph for this. Yep, here's our graph. Okay, so that's one way to get the graph really easily is just type it into Wolfram alpha. All right, so if we were to sketch this, all right, then kind of looks almost linear. All right, it's doing like one of these things where it's coming down here. So this is 1, this is 3. All right, and then we need our area, which looks like this. Now for letter B, we need a computer algebra system to be able to approximate the integral accurate to 6 places. Okay, so what I'm going to do in Wolfram alpha is I'm just going to go ahead and type in integrate sine x over x, comma x, comma 1, comma 3. All right. And it's going to tell you that it's going to give you like the psi function, but it's going to give you these values right here. Also, it gives you the area below the representation. So you could literally just type this in and get all 3 parts of A and B, because here's the integral, and then here's the approximation for that integral. All right, so we get the approximation for the integral is 0.9025, and then 69. All right, so that's for B, and then the other 2 parts are for A. Now we're going to use the midpoint rule, both with n equal 4 and n equal 8. All right, so for part C, the first thing that we should do with the midpoint rule is to try to find each of the various tick marks, if you would, or the units. Okay, so delta x for this is going to be 3 minus 1 over 4, or a half. All right, so if I'm graphing the function, okay, over here, if we were to graph it, then we were going half. This would be 1.5 and 2 and 2.5. Okay, so in the middle of this would be each of the heights. Right, and that might be the easiest way to kind of compute this. It's just by using the various heights. In this case, we're going to have 1.25, and to get that, we just take the average of those 2 numbers. And then we have 1.75, and then 2.25, and then 2.75, right? And what we're going to do is we're going to stick all of those into our midpoint formula. Okay, and our midpoint formula is going to be delta x and then the function evaluated at each of those midpoints. All right, so in this case, the integral is going to be approximately equal to 1/2 of the function at 1.25 plus the function at 1.75 plus the function at 2.25 plus the function at 2.75. Now, what I'm going to do to make this easy is I'm going to use Excel to compute these. All right, and let me show you how to do that. All right, so here's our Excel. I'm going to blow up the font a little bit so that way if you have a small screen or you're watching on your phone or something, you might be able to see a little bit better. And what I'm going to do over here is I'm going to put those unit marks. Okay, so 1.25, 1.75, 2.25, and then 2.75. And over here, I'm going to say equal sine of A1, which is going to be sine of x, divided by A1, which is x, or the 1.25. Then I'm going to hit enter, and that's the first one. And then what you could do is just grab this black box, drag it down, and then the last thing you could do is say equal sum of these values. Right, and we get 1.806. Okay, so I'm going to approximate that to 6 decimal places because that's what we did up here. So this is going to be approximately 1/2 of 1.806,062. And then 1/2 of that going to be pretty close to 0.90 actually. All right, so what I'm going to do is I'm just going to go over here into Excel and I'm going to say equal 0.5 times, it would be B5, which is our cell that we're trying to take half of. And I get 0.903031. So this is going to be 0.903031. And this is M4. So that's going to be the midpoint rule with 4 units. And that's pretty close. It's actually accurate to the hundredths place, all right, just by using 4 of those. Right? So that helps out a lot with that one. Right? And then we're going to actually find out what M8 is. Okay, so we're going to do the same thing. So we have, now remember, we have delta x first, which is going to be 3 minus 1, but this time over 8, which is 1/4. And if we have our graph, and I'm going to exaggerate this graph because we need to really find what those units are. Okay, so I know it doesn't look like that. Let me try to make it look a little better. So something like this. All right, again, not too good. Let me try one more time. If it doesn't work, then I'll quit. But it's supposed to be linear and then have like a slight curve at the end. And so this is 1 and this is 3, and we're breaking it up into quarters. So this is going to be 1.25, 1.5, 1.75, 2, 2.25, 2.5, 2.75, and 3, right? Now we have to try to find the midpoint of each of these various, or in between each of the various bases for our rectangles, okay? So when I'm drawing these, now it's going to be easy once we find like the first 2, because we could just add the difference between those each time, all right? So what I want to do is just take the average of 1 and 1.25, okay? So to find this guy right here, 1 plus 1.25 divided by 2, I think it's going to be 1.125, but over here I'm just going to use Excel, and Excel, we're going to say equal quantity 1 plus 1.25 divided by 2, and that gives me 1.125. All right, so that's going to be this guy right here, right? And then the next one, I'm going to do the same thing, and okay, I could do is I could just say equals B9 plus 1/4, because that was the delta. All right, and then I can just keep dragging this, okay, in recursive, and hopefully it's going to do what I think it's going to do. Right, so I'm just going to drag it, and then we don't want this one, right? So these are going to be each of the midpoints of each of the various rectangles. So this is going to be 1.375 and then 1.625. All right, or you could just average these. Okay, so that's another way to do it. If you don't have Excel, then you could just average each of the two and just do it by using your calculator. 1.875 and 2.125. And then 2.375, and then 2.625, and then finally 2.875. All right, so those are the various midpoints for each of our rectangles. And so now what we're going to do is we're just going to say that the integral is going to be approximately 1/2 of f at 1.125 plus f at 1.375, etc., until we get to our f at 2.875. Now, of course, what I'm going to do is I'm just going to use Excel. And what's really nice is I can just use these right here because we've already got them. Okay, so this is going to be equal to our sine of B9. Okay, so B9 is the cell. We're going to divide that by B9. And then I'm just going to go ahead and drag it. Okay. And this should be all of the heights for each of those midpoints. I'm going to add those up. So we're going to use the function equals sum. We're going to add these up. And we get 3.61074. All right. And by the way, this should be a quarter, not a half. Sorry about that, because remember our delta x. I was wondering why it was close. So this is going to be our delta x, which is 1/4 of all this. So we get 1/4, and we got our sum over here, which is 3.6107, etc. It's going to be 3.61074. And probably need one more decimal place, so it's going to be a 1 there. Okay, and if I approximate that finally, and I'm just going to go into Excel, I'm going to take a quarter of that. Okay, so that's going to be equal to 0.25 times, I think it's C18, which is our cell right here. And it gets us 0.902685. So that's going to be 0.902685. All right. So the last part of this problem asks us to be able to find the percent error of M4 and the percent error of M8. And we're going to use part B, which is this 0.9026596. All right. So the goal is to see whether by increasing the number of rectangles that we get a better approximation for this integral. All right. And we're going to see that that does happen. So just one moment while I erase this stuff so we can do that part. So just erase all this. So for our part E here, for the percent error, okay, remember, to find the percent error, you're just going to take the estimated minus actual divided by the actual, and you're going to multiply it by 100%. Okay, so and technically it's supposed to be the absolute value of everything there. So if you want to keep it like a positive. So in this case, for the error in M4, okay, that's going to be 0.903031 minus 0.902569 divided by 0.902569. And we're going to multiply that by 100% once we get the answer. All right, so just doing that in Excel. All right, we're going to have equal, and I'm just going to go ahead and punch that in. So we had 0.903031 minus the actual value. All right, and the actual value was 902,569. And then we're going to divide that by 0.902569. We're going to multiply that by 100, and that's going to give us our percent. So about 5% error. Okay, so this is roughly going to be our 0.05% error, excuse me, because we did multiply it by the 100% to be able to get that. So it's actually pretty small with respect to the error. Okay, so the error is going to be approximately 0.051187%. So that's really small. Right? Now we're going to do the same thing to be able to find the error in M8. Okay, so error in M8. We're just going to do the exact same formula, except what we're going to do is we're just going to replace the this value right here, the 903.031. So let's just erase that. And we go all the way down, and we got 902.685. All right. And so in Excel, I'm just going to go back, and I'm going to have the exact same command, all right? Except what I'm going to do is I'm just going to replace this with 902.685, right? And then this is our percent error, 0.0128, so clearly smaller, okay? So this is going to be approximately 0.012852%. So clearly we can see that M8 gives us a better approximation. Okay, so hopefully that's helpful for being able to look at the midpoint rule. And again, I know most of you have probably looked at the midpoint rule in Calculus 1. In the next section, we're going to take a look at the trapezoidal rule, and it might get us a little bit closer to than the midpoint rule to approximating our definite integral.